it's very easy to take something that's going on in one part of the country and lump it over a much larger area. And climate change is a classic example of that, because the West tends to get all lumped together in one monolithic thing. And we're not. We have very different climates between the Southwest U.S. and the Northwest U.S. Should we be concerned? And I think the answer is yes, but it's for a different reason.
Welcome back to DAM, the official podcast of Northwest Hydropower. I'm your host, Austin Rohr, and I manage all things communications here at Northwest River Partners. Can hydropower survive climate change? We talk climate change a lot around here, and it's not to scare you or to hang impending doom over your head. The bottom line is that climate is integral to both the generation and demand of energy. And looking at where the climate is headed is necessary to plan and prepare so that we can maintain a reliable grid. If we see changes on the horizon, well, then we must prepare for them. Climate change also drives energy and environmental policy in our region, and those policies have outcomes that directly impact our everyday lives. So I feel confident in saying that all of that talk is well justified. And today we're going to talk some more about it because there is a lot to talk about surrounding the question that I opened this with. Now, a few weeks ago, we had Michelle Cathcart in studio to discuss the January storm, and during that time, this topic also naturally came up. From that discussion came a recommendation to have Eric Pitlack join us here on DAM, and I'm never one to pass up an offer like that, so here today in studio to talk the forecasting of the future of hydropower itself is Eric. Thanks for joining us.
Thank you. Thanks for having me on.
Yeah, it's really great to have you here, and we're always excited to have people in studio. It's just a little bit more fun this way than doing it over Zoom.
It's a lot easier than Zoom, absolutely.
So, Eric, tell us a little bit more about your role at Bonneville.
Sure. So I'm the manager of the Weather and Streamflow Forecasting Group at BPA. So it's basically like when you see on the news a chief meteorologist, or in the National Weather Service, like a meteorologist in charge. So I manage the group that does an amazing job forecasting the weather and the stream flows that we use for power planning. So we're forecasting weather tomorrow, next week, next month, and even into the climate change space 10, 20 years from now. And then that weather information also informs our stream flows, because when we're talking about weather, we're forecasting energy demand, really. And then when we're talking about stream flows, we're talking about our supply of energy, which is water, which then we send through the turbines and use for a lot of other purposes on the Columbia River system and elsewhere across the country, because we're not the only hydropower entity in North America. There are lots of others. And we also, one of the parts of the job I love is to coordinate with those folks and see how they're using their weather and stream flow information to make decisions and maybe adjust and maybe improve their weather forecasts and improve their stream flow forecasts. So it's a pretty fun job.
It certainly sounds like it, and I think that, right off the bat, one thing I'll kind of jump into with you is, when we're talking weather, we're talking stream flows, we're making that connection. I mean, that all comes back to that really fundamental basic concept of the water cycle, and the water cycle being the thing that really makes hydropower possible.
That's right. And there's lots of components to that. And what's interesting about meteorologists and why we are needed at BPA or any other hydropower utility is there's a whole cycle to this, where just because the rain falls doesn't mean we're done with it. It's going to go into the streams and into the river systems, and we've got to manage that. And it's not the only purpose, too. I mean, we're using it for energy production on the Columbia, but we're also using that water for all sorts of beneficial uses: navigation, irrigation, fish, obviously. And also being able to control floods. That was one of the reasons why the FCRPS was established. It was not only to produce power, but the main reason is for flood control and to protect cities along the Columbia River from flooding that can get really serious in the past and can continue to get serious going forward. And with climate change, we have new challenges where the flooding is going to start occurring at different times of the year. And we're also concerned about increasing winter flows. And we're a little bit different than the Southwest U.S. or in other parts of the West, where with climate change, it's actually more likely than not our precipitation is going to increase, not decrease. But then you put that on the other side about having longer periods of low summer flows when the snowpack is melting earlier. That creates different challenges. So, and we always have to stay up with that. So forecasting weather for tomorrow or next week or 2 weeks from now is not that much different than forecasting what the climate's going to look like 20 years from now.
And I think maybe people that haven't learned to love our rain here in the Northwest are shaking their fists at the sky right now, hearing that we got more precipitation coming.
Yeah, and a couple of things there. One, I call it rain equals revenue for us, but that's not quite true because just because it's raining in the Pacific Northwest and Portland and Seattle does not mean we're not dealing with problems elsewhere in the system, because where one part of the system in the Columbia River Basin is quite large. We're going from the Canadian mountains all the way down to the Snake River Basin and semi-desert areas. That's very different climates, and just because it's raining in Portland doesn't mean we're getting snow in the mountains that feed the Columbia River system, and vice versa. We could look really sunny and dry here, but if it's snowing a lot in Canada and Montana, then our water supply situation is very different.
And so just kind of, before we dive in too deeply, I do want to touch on as well, how did you get started in forecasting, and what is it like tying that sort of background into this energy space?
Well, it's interesting because I've wanted to be a meteorologist since I was about 5. I was one of those kids who saw the weather people on TV and wanted to do that. And that has continued. So I'm pretty lucky that I'm doing what I wanted to do since I was a kid in my career. But I started off with wanting to get into broadcasting, changed over to really being interested in actually watches and warnings and National Weather Service kind of things. And I was in the National Weather Service for 21 years. And during the course of that career, I started developing a really strong interest in hydrology, first in Iowa and then down in Arizona. And then realized as I started hearing more and more about climate change and getting more experience and education on it, and realizing, wow, this is going to be a real thing, I really started getting interested in the climate change, meteorology space in terms of policy. And then what happened was Bonneville Power Administration, this job came open, and I was like, well, this will be interesting. And luckily was selected for it. And so I've gradually come to this space. I started off, and still am at heart, a meteorologist and a weather nerd. But seeing how our weather forecasts, our stream flow forecasts have a direct impact on system operations on the Columbia system, to optimize it and to maximize the beneficial use of that river for all purposes. That's been really a fun job, and it's always changing. Weather's always changing, and now we have to deal with not only is the weather changing, but the climate's changing too. And so now we've got to worry about two things as we're putting together our forecast going out, again, days, weeks, months.
And, broadly speaking, I want to ask, what is weather forecasting? Because we see the weather guy on the TV.
Sure.
At least I hope most of us have by now at some point. And I'm sure some people have, said, oh, that guy said it was going to snow tomorrow and it didn't happen, or, things like that. But as far as the actual, practice of forecasting, is that primarily, let's say, modeling? Is that primarily, looking at the past? How does that really work on a sort of 35,000 foot level?
Broadly speaking, weather forecasting is predicting the weather. We've wanted to do this for thousands of years as a human species, and the good part about that is that over the 19th and 20th century, really smart people who were physicists and engineers basically derive what we use as our equations for the atmosphere and how it is governed. So those fundamental calculus differential equations are known, which that's an advantage. The problem is, if anyone's an engineer out there, they're differential equations, which means that you need to have data at every single point in the atmosphere to adequately and accurately predict what is going to go out and happen in time. Well, we don't have that information. 70% of the world is covered by oceans. We have satellite data, that's getting better, but we don't have observations every single point in time and space. And so what that means, though, is now we've got to extrapolate, and that's where models come in. That's where an understanding of the atmosphere and how it's supposed to work on a kind of on a qualitative level helps. So fundamentally, meteorologists are, and hydrologists for that matter, are engineers, statisticians, computer scientists, all rolled into one. And there's a certain amount of art to it, too. Because we don't know what's going on everywhere at all times in the atmosphere, and we're still learning. That's the other part that's been really exciting.
And I think that we've maybe touched on a little bit already why something like this might be valuable to a utility or to public power as it relates to the value of being able to forecast these things. But how does that work impact a utility's operations and play into some of the things that they're doing when it comes to hydropower generation, or even just trying to understand how much energy is going to be available to them in the future?
There's a lot of levels to that point, because how it impacts the utility, it can be huge. Virtually all large utilities, by the way, in North America have meteorologists on staff, just because everything is so complicated, or they contract that out. Smaller utilities tend to use what's available to them. And I'll give a plug. My previous employer, which was the National Weather Service, they're a great resource for weather information too. And we use the same weather models that the TV meteorologists use across the region to make forecasts of what's expected to come. For a utility more specifically, at the very least, we're forecasting storm impacts and energy demand. So when we were dealing with the January cold snap, that wasn't just cold, that was ice, it was high winds, and that can impact not just generation, but the transmission lines. So we're forecasting that, but then we're also using that weather information to forecast our stream flows, which I mentioned earlier is our fuel supply. So we're forecasting both sides of that supply-demand equation. Again, when we're talking about renewable energy, which hydropower is, wind and solar is also weather dependent. And as we get more wind and solar onto the grid, weather forecasting is going to become even more important than it already is for energy production and being able to project what's available to us. We've got to be able to forecast more than like an hour in advance. Okay, are we expecting 2,000 megawatts from wind today or 4,000? And that's going to impact other generators across the region. And so weather plays a role in projecting all that. So that's basically why we're valuable, and why a lot of other entities have meteorologists as well.
Yeah, it absolutely makes sense, and I'm sure on even the demand side, it also makes a lot of sense because you have things like a January storm where everyone's going to be running their heaters and trying to keep the power on, trying to keep everything going, and the end result of that is obviously more draw on the system.
That's right, and heat wave as well. And with climate change, we are expecting more intense, longer heat waves, and possibly even more frequent heat waves. With climate change, though, we still get cold, and it may occur a little less often with climate change, but hydropower utilities, or any utilities for that matter, have to prepare on both sides of those equations as we go forward with climate change.
And just a quick, clarifying thing: is it safe to say when we're having this discussion that this is the reason why we've phased out the term global warming? Because we're not just talking warming. Really, we're looking at the entire situation, both cold snaps, heat waves, and everything that happens kind of throughout the year on a cycle.
That's a really good question. I'm not exactly sure how the transition from the name global warming to climate change evolved. There's probably a paper out there that does tell that history on that. But the realization is that it's not just the globe that's heating that's the problem. It's all the impacts that that's going to have. And the biggest one actually is on sea levels. And when you look at geopolitics and where half the world's population lives, it's pretty close to sea level. And sea level rise is a very likely, in fact, near certain outcome with the temperatures that are warming across the globe. So that's one of several components that climate change is going to impact one way or another. And so I think when you're mentioning climate change, you're talking about the whole spectrum of what we're expecting as the climate continues to warm. And hopefully, by transitioning the grid and general decarbonization of our, just basically globe-wide, we can bend that curve and get to a point where we have, we can level off what we're seeing.
And so when we're looking at short-term, long-term forecasts, we're looking to the future with climate change. What are some of the factors that we're putting into some of these different models? I mean, what sort of variables really shift things one way or another, or maybe create variability such that you can't say a forecast is just black and white, but there's some gray in there where things are going to potentially steer this way or this way?
That's a great question. And the issue there goes back to, while we know all the fundamental equations of meteorology and hydrology, we need to have data at every single point on the entire globe surface, and we don't have that. So we have to rely on really good observational networks that are getting better and better over time. We're using technology from the late 19th century. Weather balloons are still very valuable to us, believe it or not. You'll see them launched every once in a while if you know where they're launched from. They go up at least twice a day to give us a sample of the atmosphere. Surface observations, when you fly into PDX airport or SeaTac, and you'll see weather sensors around that airport. Those are weather sensors along with tens of thousands, hundreds of thousands of other weather sensors across the globe are going into computer models to inform, okay, what's the state of the atmosphere now? What does it look like going forward? Radar, that was a big advance that came out of World War II that has gotten better and better over time, and now has really improved our ability to warn with tornadoes and flash floods and severe thunderstorms and snowstorms and that kind of thing. That radar data is important too. Satellite data, that's also getting better and better and better. You put that all into a complex set of weather models, and you're going to get a different set of answers depending on the type of weather model, what its purpose is. There's a lot of things that go into numerical weather prediction, and you get what we call an ensemble or a set of forecasts. And we, as meteorologists and hydrologists, will take that ensemble, which is basically a range of potential outcomes, and not only make a single forecast, which is called a deterministic forecast on, that's the one you hear, okay, we're going to be partly sunny today and 57, or we're going to get 2 inches of snow today. That's a deterministic forecast. But there's always a range around that. In some cases, the range is very, very large. Sometimes it's very, very small. It just depends on the situation we're dealing with. And that practice that we use for meteorology and hydrology, we also use in climate change as well. We are very sure, 100% sure, that we're going to continue to warm through at least the mid-21st century and maybe beyond, depending on what we do in terms of carbon emissions. But we know that range in temperature increase is somewhat large. Depends on where you are in parts of the region as well. And then we add that heat to the atmosphere. That's now increasing evaporation from the oceans. That puts more water into the atmosphere. That affects precipitation. And so now you can see how suddenly it gets very, very complicated and how you end up with a pretty large range of potential outcomes. So that's why we can't say with certainty in some areas of the climate change space what's going to happen going forward. There's certain things we're very sure of, like temperature rise and sea level rise. Less sure about precipitation. Wildfire is an emerging area that we've got to be more careful with, because now we're getting a better understanding of the heat on the ecosystem and what that's doing. And when you heat up an atmosphere, you're also drying it out in some parts of the country, and you can make that fire risk worse. So there's a lot of things that go into trying to forecast what's going to happen going forward. And again, it's usually a range of outcomes, not necessarily one answer.
I mean, even to build on that a little bit, I know, for example, having seen it, experienced it firsthand, those areas that are stricken by wildfire, for example, then become maybe destabilized due to the fact that the vegetation has died off, and you can experience slides, you can experience things like that. I would have to imagine that maybe even plays into the path that water is going to take to get to a stream, or move through the watershed, and also potentially how fast. And that kind of leads me into this question of, are there additional variables that maybe we can't include because they're too challenging to include, or there's too much variability, or they're so, kind of niche that they just don't wind up in those models? Are there kind of things outside of the climate model that get that play a role, but we can't necessarily always predict very well?
That's getting better in the sense that as a meteorologist, I want to incorporate all the processes that go into the meteorology so that we can make a better forecast. When we talk about wildfires, that area of hydrology has actually advanced pretty quickly, and that we understand that in areas where we have high intensity burn areas, it fundamentally changes the soil characteristics, that the runoff occurs much faster, and it takes time for that soil to recover, sometimes on the order of a decade, before the runoff returns back to a different normal. It's not the same normal, but a somewhat different normal. So in terms of hydrology and fires, we're getting a better understanding of that. Same thing with atmospheric models. We're now understanding that you can't run a weather model unless you know what's going on with the ocean. You can't run an ocean model unless you know what's going on in other parts of the ocean. You can't run a hydrologic model unless you know what's going on in the atmosphere. You can't run, and you can see land surface. One of the other areas that I've taken interest in is we know that with climate change and you're heating the soils up, are you drying them up? And if you're drying them up, does it make it harder to rain in some parts of the country? And that's why that whole idea of aridification is a concern when it comes to climate change in certain parts of the world, because that feedback loop could intensify. So there's a lot to learn, and that's the kind of the neat thing about my job, is that we're always learning and trying to incorporate. We know how those fundamental equations work. We just got to make sure that we incorporate all those inputs, and sometimes the inputs are a little bit harder to gather. You brought up one that you asked for an example on where it's still too hard to incorporate. The area that I'm really interested in right now is snowpack monitoring, and how just 10, 15 years ago, it was very, very much centered on what's going on at individual observation sites. We call them snow pillow sites or snow tell sites. They're basically stations that are scattered across the Columbia Basin and across the U.S. actually, but mostly in the West, where they are measuring snow as it falls, the snow water equivalent in that snow. But we only have so many of those, and they don't cover all areas. So the interest in satellite imagery comes up. Satellite imagery could really help us out there, but we have these things called clouds in the Pacific Northwest that tend to shield our ability to really look at the snowpack going on underneath, and so you get glimpses, but not all the time. Now we're developing airborne LiDAR technology. A lot of folks have been working on that over the last few years, and you can actually fly over areas and get snow water equivalent over an aerial basis versus points. That's showing some real promise, and if we can somehow leverage all that new technology in terms of remote sensing, we might get a better and better understanding of snowpack, which is critical, absolutely critical for the Columbia Basin, because we are a snowpack dominated system. And understanding what that snowpack is doing, not just this month and this year, but with climate change, is absolutely important to us. I'm excited to see how that evolves.
Yeah, that will be very interesting, and I think one thing you brought up within that I'll just call out quickly is the use of LiDAR, and that's a technology that's evolved so much, and
Yep.
and I think if people are hearing that and they're like, "What the heck are you talking about?" I mean, if you've got a car that maybe has like auto cruise control or different things like that. I know a lot more cars are incorporating basically a LiDAR sensor of some kind that can help
That's right.
help do things like that. And so, in the same way that I'm sure that that's evolving and changing over time, that technology is probably evolving and changing in a lot of other ways to be able to do a lot more than maybe people realized it was capable of.
Yeah, no, that's absolutely right. And, another area that's good to point out is what's old is new again in my career. I remember when I was a baby meteorologist in the late 80s, early 90s, hearing about this thing called machine learning and artificial intelligence and how it was going to save the world. Well, it's back again. And it's back in an exciting way because our computer power is infinitely better than it was when I was a baby meteorologist. And to see how that can be leveraged to improve our weather models, our streamflow models, that's going to be exciting. Now, we have to be a little careful because it's also very easy to create a black box. And, it's also very easy to develop what I call snake oil, where you develop the AI model. Look, it works. Well, how does it work? I don't know. It just works. That's not acceptable to a meteorology scientist. But there's some really interesting areas that we think that AI and artificial intelligence, and AI and artificial intelligence are the same thing, but machine learning could help us improve our weather models on the input side. Like I said, we've got a lot of data that comes in, but we don't have perfect data there. But we also have to post-process things that once we run a model, we sometimes have to tweak and correct its outputs. There's good ways and bad ways of doing that, and machine learning might be able to help us do that. So I'm excited about AI and machine learning as well in the meteorology and hydrology space.
Yeah, it will be really interesting to see. And, right now, a lot of people are using AI for all sorts of, silly things, maybe, at least in the mainstream. ChatGPT has risen to popularity very quickly. And we've actually discussed a little bit on this podcast as well, the potential energy impact that all this AI has in terms of the data centers and how much it takes to keep those things up and running. But it'll be very interesting to see how it can be used as a tool to really help us in these kinds of areas.
Yeah, and then I think you're going to see it more and more in the climate change investigation space as well.
Yeah, it totally makes sense. When it comes to taking all of this input in and actually determining our stream flow and really understanding the availability of energy that we have coming our way, how does all of that come together and work?
So the one thing that's really neat about BPA and my group in particular is that when we produce a weather and streamflow forecast and say we're done, here it is, our work doesn't stop, because that has to go, the weather forecasts have to go into our energy demand planning models to figure out, all right, so how much energy demand are we going to have to meet today, tomorrow, next week? It's also going to go into our planning area where they've got to take the stream flows and the energy demand forecast and then true it all up and then determine the best way to operate the system. And so when we put out a weather and streamflow forecast, a couple hours later, we're seeing the impacts of that in terms of the planning, in terms of the decisions that need to be made. And sometimes the questions will come back to us like, well, all right, so how certain are you that that's going to happen? Are you really certain or not certain at all? And having a group that actually tolerates an answer going, I really don't know what's going to happen 2 weeks from now. And they get that because there's certain weather situations that happens. Being in that environment is really great, and it's really gratifying to get that feedback. You also know when your forecast is wrong too. You're going to hear that too. And I think that's valuable too, because that keeps our pencil sharp and makes us, oh yeah, this has got real impacts. So we better either do a better job or figure out what happened there, or better quantify or better explain the uncertainties involved in certain forecasts that we do. And I'll skip to the cold snap a little bit. That cold snap was really interesting in January, other than, well, it was the worst one we've had in 20 years. So that was a starter. But we look back, and in 2004, that cold snap had maybe 3 or 4 days lead time. Maybe. It was a little debatable. This one in January of 2024, we had 12 days of lead time. big difference. And that time allows you to do some things that you can prepare for that we couldn't have done 3 or 4 years ago, or even, 20 years ago, let alone 3 or 4 years ago, where you just have to react. In this case, you can be proactive and position the hydropower system to get ready to buffer what's to come. And, we were still uncertain about the exact magnitude 12 days out. At least we knew something was coming and that we could start making some adjustments. So same thing happened in the 2021 heat wave. We knew that was coming, and we had good lead time on it, even though it was an all-time record. That little advance notice gives all the utilities and BPA time to plan, and we've got a great hydropower system that we can use to plan for that. That we can hold some water back, or release water, or move things around, or move outages around, or work together to make sure that everyone's lights stay on. And having a little bit of advance notice goes a long way.
And when it comes to that advance notice, do you think that the difference between, say, a 2004 example like you gave and the one that we just had is that what's happening in the atmosphere is more predictable? Maybe the conditions are setting up so that you're more certain one way or another, or is that the result of better modeling, better technologies, a better understanding, being able to provide us with more lead time?
That is definitely a both question, or both answer, where our weather models are getting better and better and better all the time. I think about the old radars they used to work on in the mid 1990s, and look at radar imagery now. It's night and day. Satellite imagery, we can get satellite imagery every minute if we need to. Back 30 years ago was every 30 minutes. So that part has we're getting more and more data. Sometimes it's a little too much data to digest, but a lot of data. The weather models are getting better. And our understanding of the atmosphere is getting better too. There's a lot of very smart people working on meteorology and trying to advance in hydrology, our understanding of, okay, so where's that? Okay, we're seeing this weird water cycle thing going on here in, let's say, the Upper Snake. Is that water disappearing into the aquifer, or is that showing up somewhere else? And now you have to do a study to figure out where's that water going. Or, well, that's interesting. The model's behaving differently when we have a snowmelt in June versus May. What's causing that? Okay, let's dig some more. There's some really good work being done so that we can improve our ability to forecast. And the results speak for themselves. So I look back at our internal verification numbers, and weather forecasts issued 5 days in advance right now are now as accurate as 2-day forecasts were back in 2014. So the idea of just 10 years, we can now forecast out to 5 days with the accuracy that just 10 years ago we only had at 2 days. That's pretty impressive. The other one is we're starting to get skill, at least on our day-to-day temperature forecast. We're getting skill over climatology. In other words, if you just let climatology do its thing and you know what your average high and low temperature is and you forecast that, versus the meteorologist in the models saying, okay, we're going to, it's going to be 5 degrees above normal or 7 degrees below normal. Our skill now is all the way out to day 14 on that, and it's increasing. Even on the seasonal scale, we knew this winter, because of the El Nino, we had a very strong chance of having an above average temperature winter. That played out despite the cold snap. So that skill is increasing, and hydrology is in the same situation and gradually getting better and better over time.
That really leads me to this next question that popped into my head, and that's, in the context of the climate change discussion particularly. So we're looking at something 5 days in advance, 14 days in advance, things like that. But we know, as you're mentioning just now, you can look to maybe next year and say, I think we're going to have an above average winter. When you are looking at an El Nino winter, or we're going to have a really warm, dry summer come 2025, things like that. Do the extreme weather events show up at all, or I mean, is there like a probability of we're probably going to have at least one cold snap or one heat wave during that time period, or are those things that really only show up on those shorter term models?
That's a mixed answer there, and it depends on what we're talking about in terms of is it temperature, precipitation, snowpack, streamflow. For example, even though the forecasts turn out to be very accurate that we're going to have a warm winter in the Columbia Basin, it never eliminates the possibility that you're going to have a quick, sharp, cold period like we had. Conversely, same thing can happen where you can have a cold, rotten winter, but you get that 1 week in March that gives everyone hope, and then it gets cold again. So just because you're going to have a whole season that's going to be above or below normal doesn't mean that it will necessarily eliminate the possibility of a more extreme event. However, if we are in a very strong El Nino situation we have this year, that is an atmospheric river situation for California, where a series of them can hit them in rapid succession and cause a lot of flooding and heavy snow. It's great for for water supplies, but not great if you're dealing with flooding. In an El Nino, if you know that you've got, okay, here comes one, wait a minute, there might be more coming because the whole Pacific Ocean, the tropical Pacific, is warmer than normal. Okay, we got to watch out for these. And now okay, so if I start seeing one, there's going to probably be more. Same thing with a La Nina, by the way. If we get into a La Nina, and that increases the risk of a below average temperature here in the Columbia Basin. Now we're watching the Arctic very closely because we know that chance of getting an Arctic air mass and a cold snap here, despite climate change, by the way, increases when you're in a La Nina. So it can work in multiple ways. But the other thing that's really important to point out is just because you have one heat wave does not mean that's climate change. But if you start seeing more and more of them, hotter and hotter ones, more frequent ones, that is. And that's one of the things that we look for in the region and that we're already starting to see. Other parts of the country, longer dry spells, particularly the Southwest U.S. One dry spell is not climate change. One drought year is not climate change. But if you start seeing them in succession and you start seeing that, well, wait a minute here, these are coming with the increasing temperatures as well, we got to start taking a look at that more closely. Then it probably is climate change. So that's one of the other things we're a little bit cautious about, is attributing one event to climate change. That attribution science is getting better, but not one event is not caused, quote unquote, by climate change. But you get lots of them, then you got to really start really beginning to wonder at the very least, but possibly really dig in to see if this trend's going to continue.
Yeah, I really appreciate that distinction. And, the question now is like, okay, so we had this event in January, and we know that not only did it deliver snow, ice, cold temperatures, all that, it also put a lot of strain on our energy demand. And in turn, we used a lot of hydropower to step up and meet that demand. When something like that does take place, how much is that disrupting the outlook for the rest of the year and for the season as it relates to particularly the streamflow component? And, not so much in our maybe run-of-the-river dams, but in those dams where we're having to potentially tap into some of our reservoirs and use up what's there. You're looking ahead and seeing, how much of that's going to get replenished later on in the season. I mean, is that like a big disruption, or is that kind of a blip on the radar?
It depends. That's a really good it depends question. And that's one of those where that's why there are really, really smart planners at Bonneville Power Administration, that they're the ones that are the ones that figure out, okay, this is going to impact us. We're going to have to ramp up. All right. What's the impact now later on this spring and summer in terms of our fuel supply? I defer to them on that stuff because they're the experts. But in terms of the weather and the stream flows, a cold snap like that doesn't necessarily mean you're going to be hurt for the rest of the winter, or a dry couple of weeks doesn't mean we're going to have a low water year. What we're looking for is the cumulative effect of that over the whole season. The other thing too about again, the Columbia River Basin is unique. I wouldn't say unique, but it is a marvel of the Columbia system, is that it's a large geographic area with a lot of geographic diversity. So just because we've got an impact in one area doesn't mean the rest of the system is affected. And that's one of the reasons why hydropower has been so reliable and probably will continue to be even with climate change. Because even if the Snake River Basin, that does look like, the whole basin looks like it's going to get warmer. But as precipitation in the region increases, particularly in Canada and up in the northern parts of the basin, that can insulate us quite a bit. And then conversely, let's say we're having a dry winter in Canada, but the Snake River Basin's okay. That can also balance things out. So because we've got a large geographic diversity, that gives us a lot of insulation from shocks when we get a cold snap or a heat wave.
That certainly makes sense to me, and I'm thinking about some of those rivers maybe on the East Coast and things like that, where they don't necessarily have Cascades or Olympics or Rockies or all of the different mountain ranges we have here, where I think I assume that's where a lot of our snow is kind of being stored.
It is. It's being stored in our very beautiful mountains.
Yeah.
Where in the eastern U.S., the southeast U.S., you have virtually no snowpack ever, except from an occasional storm. The northeast U.S., the snowpack does have an impact, but it tends to be smaller than it is farther north in Atlantic Canada or southeast Canada, Quebec, Ontario. They also rely very much on snowpack for their water supplies. But our mountains are a valuable resource, and they are our biggest reservoir. Really, that snowpack is our biggest reservoir, and that can hold that water back for several months. If it melts nice and slowly, we have that water for several months into the summer. And again, it's not just for hydropower. It's beneficial for fish. It's beneficial for navigation. Beneficial for the irrigation that we need for our crops in the region. So that reservoir is very important, and that's probably one of the biggest risks we have with climate change, is that snowpack becoming less and less reliable, particularly in the southern half of the basin, where more precipitation going forward with climate change is going to fall as rain instead of snow. Or it'll rain, snow, and that doesn't give you a reliable snowpack. And we see that in the Cascades already, where you'll get a couple weeks of rain and it just melts a lot of snow off. We get flooding, and then the snowpack starts building again, but then it rains again, and then you keep going back and forth, and that makes it harder and harder to forecast stream flows, because now you don't have that reliable, that snowpack's going to be there for a few months and then it'll come off, hopefully gradually. That's one of our biggest concerns with climate change, is that snowpack becoming less and less reliable for us, not just for prediction, but just for the river flows themselves.
One of the big things that has sparked us having this conversation today was the topic of climate change and the threat it poses to our energy supply. A lot of that relating to this snowpack discussion and the challenges that climate change presents when it comes to having a reliable, predictable snowpack, and one that can power us through the summer by melting off gradually and slowly, as opposed to what you're describing, this sort of quick, rapid runoff that takes place. Many people are concerned by what they're seeing, I think particularly in the desert Southwest. And as I was preparing for this podcast this week, AI must have been listening to me on my phone, because I saw probably 5 or more articles come up in my news feed that were published just this week as we're recording, that all basically said drought and climate change are heralding the end of hydropower in the West. And this is being brought up so often that people are really, whether or not they actually should be, they're feeling very concerned because of what they're seeing. The question is, are those concerns valid? Should we be concerned about what drought means for our hydropower here, particularly in the Northwest?
So, as you've probably gathered, meteorology and hydrology are pretty complex. So is climate. And it's very easy to take something that's going on in one part of the country and lump it over a much larger area. And the climate change is a classic example of that, because the West tends to get all lumped together in one monolithic thing, and we're not. We have very different climates between the Southwest U.S. and the Northwest U.S. And so the responses to climate change in terms of how the atmosphere is going to behave, how the soils are going to behave, how the river is going to behave, how the snowpack is going to behave, is also going to be different. Should we be concerned? And I think the answer is yes, but it's for a different reason. And the Southwest U.S. is really dealing with a long-term drought that's been going on for 20 years now, made worse by climate change. And that's not easy to deal with. And even if the climate gets wetter down there with climate change, evaporation's increasing with temperature as well. And there's a real question, scientific question, on whether the evaporation is going to increase more than the stream flows as the climate gets a little wetter and you start getting more heavier storm system and heavier rains from individual storm systems. In the Pacific Northwest, we have a different problem where we actually think, or it looks like, that precipitation is going to increase in the region because we already get atmospheric rivers, those ribbons of moisture that give us the majority of our rain in Portland and makes some days pretty miserable around here, and quite memorable because it can rain really, really hard with some of those. Those with climate change are likely to carry more moisture because oceans are warming up. They're releasing more moisture into the atmosphere. That feeds into atmospheric rivers. That should increase our precipitation on a winter basis. But if that's falling as rain or snow rather than snow, that becomes a problem in terms of the hydrograph and where the stream flows are occurring, where instead of seeing not a lot of water in the rivers in the winter, it's likely we're going to see more. Now, for hydropower, that might be good in the sense that that will give us more generation, and with temperatures not warming over time, you still get winters like you did here this past January, but for the most part, those cold snaps become less and less frequent. Okay, so that may help mitigate one problem that we already have in the basin, which is we can have some really big winter peaks. But then you melt that off early, run it off early, and now your period of low summer flows when it's already dry in the Columbia Basin. July, August, that's why people love it here in July and August, because we don't rain. It's beautiful. But if you extend that period to, you basically run off all your snow in April and May instead of June, now that period of low summer flows we used to have in just August and September now becomes a July, August, September issue. You're lengthening that period of low summer flows as temperatures are warming and as energy demand, especially from air conditioning, is increasing. So we have a different problem, and that we need to definitely address and be concerned about. And that's why discussions about resource adequacy are going on, and making the whole grid more climate resilient, because our problems are different than the Southwest U.S., but they are no less serious in that we have to prepare for them.
And my understanding, and correct me if I'm wrong, my understanding is that in addition to there being a change in the timing of, let's say, generation, because that rain is going to hit the system more immediately, which means there's more to generate as the rainfall is happening, but not later in the season.
Right.
I also understand that when we're looking at climate change, the prediction shows that there's even sort of maybe a shift in timing seasonally. Right. I think you touched on it a little bit of starting to get into September now. I even think not last year, but I believe the year before, I was still wearing shorts and a t-shirt in October. You know, we were almost hitting 80 degrees there until nearly the end of the month. How much of that, sort of timing thing are we looking at, as we get maybe a couple of years down the road or even greater?
Well, keep your shorts handy for Septembers and Octobers, because with climate change, the falls are getting warmer. It is unclear when we get into the fall, because we usually start getting rain in October. Does that mean the rain will be delayed? Or does that mean the rain, when it does start in October, is going to be heavier? So now you're wearing shorts and in a very humid atmosphere, in a humid environment, and now it's raining harder, heavier, on soils that are very dry. Now you got more runoff. Those are the questions that could factor into the fall. My biggest concern is actually going into falls is what's happened to our fire season. And I look at California and how their fire season now has become an all-year problem. Here in the Columbia Basin, fire was only about a 2 to 3 month concern. Now it's a 4-month concern. With climate change, that's going to get longer. And that has an impact on BPA in a different area, which is grid resiliency. And, Michelle Cathcart, who was here on the podcast a little earlier, she was instrumental in actually developing the wildfire plan at BPA, and a really, really smart group of people in transmission operations and transmission, our field orgs, to make our grid more resilient and take a really hard look on, okay, so where are we looking in terms of what areas are we going to have to increase our right-of-way or be really smart about our vegetation management? What parts of our system need to be hardened for wildfires? And they're really taking a very scientific approach and targeting the areas that are most at risk, because this wildfire issue is not going to go away. And this is a really good example on having an agency like BPA take a good hard look at things and go, okay, here's the threat. We've got to really look at this in a serious way, because this is not going to get better. And let's go ahead and make our grid more resilient. And, and you see what's going on with the wildfires in the West. And with the fire season getting longer in the Pacific Northwest, that is going to become a problem here. The way I like to think about it is, instead of rolling the dice 2 or 3 times a year, you're going to get a bad fire. Now you're rolling the dice 5 or 6 times. And I don't like playing those odds in Vegas. And I certainly don't like to play them with wildfires or with our atmosphere.
I can't say that I know a single person who's a fan of wildfires.
No.
So,
yeah.
And that obviously includes the people who fight it.
Right.
Job security, but at the end of the day, I don't think that they're by any means fans of it.
Well, no. Yeah.
And it's something, it's a little bit kind of a detour here, but I do want to ask quickly, because we've had some folks on the podcast in the past, particularly utilities, who have talked about their kind of different wildfire strategies. And one in particular was Consumers Power, who firsthand experienced the destruction of like the Detroit area in Oregon and everything like that. If maybe a BPA customer, a utility served by BPA, is starting to think about implementing a wildfire plan and they haven't, or maybe the thing is outdated, it needs to get dusted off type of thing, is that something they can reach out to you guys about?
Yes. I think our transmission operations folks would be glad to chat with folks. And, I'm glad you brought this up, because we meteorologists are doing the same thing. We are collaborating quite a bit with our utility meteorology friends in Southern California, because they have much more wildfire experience than we do, but we're scrambling up a curve for better or for worse. So we've got to get more experience quickly. So we're asking them how they're doing things. Eastern U.S., when they deal with heavy snows accumulating on trees and bringing down power lines, they have a lot of experience in that area, because they have deciduous trees that like to attract snow and hold on to it and fall on a line. We're picking their brains about how are they forecasting that, because our snow is a little different. It tends to be a little drier. It doesn't tend to stick to trees. But is that going to be an issue with climate change? We don't know, but let's find out what they're doing in case it does become an issue for us. So we're sharing best practices. Hydrology is really good about that, because not only do we have hydrology forecasters at BPA, we have hydrology forecasters at BC Hydro too. They're right across the border. We share not only the Columbia River system, but we share a tree. We're collaborating best practices too. It's been great to work with hydropower utilities in Iceland and Manitoba and Ontario that, snow-dominated hydropower systems too, how they're improving their hydrologic forecasts and their best practices. So we're sharing best practices just like I hope utilities are sharing and transmission folks are sharing best practices between each other, and it's going on. In terms of wildfire mitigation and resiliency. That's one other neat thing about our industry is that we're trying to share this information as best we can. And a lot of people are very, very open to do that, and we're going to learn from each other.
I do have to ask as well, when we're talking about this topic, and I believe, if I understood you correctly, we're not terribly concerned about evaporative loss in the Northwest as it relates to threat to hydropower, but I assume that there are maybe some particular areas within the basin, being as large as it is, where maybe we could see some of that taking place. I mean, is that something where having a dam can help to mitigate against some of those extreme temperatures and evaporative losses? Or is the opposite true? And part of the reason I ask is I remember an example, I think it was from the Fraser River Basin, and I don't remember the exact tributary, but it was either last year or the year before that I saw some news had come out about the river basically drying up to the point that it was impassable for fish. And so it is kind of a question of, in maybe those more localized areas, does having hydropower there, does having more water built up behind a dam help prevent some of those evaporative concerns?
I would say that is probably the most active area of research underway, right next to getting a better understanding of water temperatures in a river system. Both of those are very complex science issues. And remember I said very early on the podcast where we understand the equations and we know the inputs. We just don't have the data to do that. We actually don't have a ton of data when it comes to evaporation. And there are different ways of measuring evaporation. And methods that were, just putting a pan out and measuring the amount of water evaporated in a day. Very low tech, good, because it gives you at least a start. But there's also the amount of water is being taken up by vegetation and being pulled into the atmosphere. And that are put back into the atmosphere. That is good for the tree in the atmosphere, but that's pulling water out of the ground. That is an area of active research, and it's unclear if dams help or hurt in this area, just because our evaporation is lower because we're farther north, and we are cooler in the Southwest U.S., and our humidities are a little bit higher. The Southwest U.S., though, they really watch that closely, and that is probably an area that, at least in the Department of Energy research, has been showing that evaporation is on top of drying soils, on top of just having a lack of precipitation, and even if that precipitation reverses and it does get wetter, you have all these other things going on that is a real concern. Because again, they're hotter, longer, lower humidity. Here in the Pacific Northwest, not as hot. We're getting warmer, but not to the extent of the Southwest U.S. And our humidity levels are a little bit higher. But evapotranspiration, evaporation, and how climate is impacting that is an area of active research. We do know with temperature increasing, though, evaporation increases. That we do know. But the question is how and how much, and is that offset by increasing precipitation? And if you have increasing precipitation, does water storage behind a reservoir help you or not? But if you create another body of water, you're also creating evaporation potential. And a lake, you evaporate because of more surface area. There's more evaporation from a lake or reservoir than there is from a narrow river. Both have evaporation, though. So complicated question, but an area of active research.
And very important research, might I add.
Yeah, and this goes right up there with water temperatures as well. And we're talking about endangered species. And by the way, water temperature is also an issue for energy because you need, in a lot of places, you need cooling water for thermal plants, so including nuclear. So water temperature is a question that is a big research issue because we have the observations, but the modeling is not that great. And the modeling is advancing, but it needs to advance a lot more and to get it down to the granularity that we need. Our water temperature, good example is actually over the ocean. We actually have a decent idea what water temperatures are over the ocean, but we don't have a really good idea of how warm the water is underneath the surface of the ocean unless you've got a buoy array, which we happen to have in the tropics to monitor for El Nino. And you can watch and see, okay, so this sensor is 200 feet below the surface of the ocean. Okay, it's monitoring temperatures here. We don't have those over the whole ocean. Throw that into a river system where you have reservoirs that some of them stratify, some of them don't. Tributaries that are feeding cold water in from a very deep aquifer. Oh wait, this same stream, but now it's tapping from a shallow aquifer, much warmer water, or rapid changes in temperature for the same stream because it's not getting fed from underneath it. Water temperature modeling is really hard and is an area again of active research because we need it. We need to understand what our rivers are doing in terms of water temperatures and for a variety of reasons, not just fish.
And just quickly along those lines too, and I say this more anecdotally because just because of my own outdoor recreation experiences, but I imagine the same kind of conversation about rain versus snow plays into this because you can definitely tell when you're near a body of water that has been fed by snow and ice recently as opposed to one that's not.
Yep. Absolutely. And when that snow melts has an impact as well. And we were talking about earlier with climate change, with snowpacks melting earlier or being less reliable. That can affect water temperature as well.
I think it's safe to say that throughout this conversation and especially this last few minutes that we've discussed this, the idea that climate change is signaling the end of hydropower as we know it is probably not accurate. But from your perspective, what is the most likely outlook for Northwest hydropower in the face of climate change?
It's going to change. That's my most likely outlook. And that's a terrible meteorologist answer, isn't it? It's kind of like it's going to rain sometime this winter in Portland. I mean, that's it's going to change. And like I explained earlier, it's the timing of the water that's going to be issue, not less of it. We're not looking at other parts of the country where they are going to have less water going forward in terms of runoff. They might get more rainfall, by the way, but have less runoff. That's a whole other story. But in our case, it's the timing that's going to be the issue. And having both when the fuel arrives and when the demand is highest is changing, and that rate of change is not 100% certain because, again, climate, just like for weather forecasting, climate forecasting has also got this range of outcomes that can occur. It's going to change, and I think the best thing that we can do is to stay on top of it, stay on top of the science, stay on top of the good science, because there's some bad science out there too. Stay on top of the good science, really work with people that are, really climate experts, hydrology experts, weather experts, to improve our science more broadly. I think that was going to go a long way to making our hydropower system resilient and keep it part of the equation for a long time to come.
Along those same lines, what does climate change look like for our other renewable resources, especially talking about wind and solar?
Very unclear, because this is a great example, and we're very sure about temperature changes. We're less certain, but pretty sure about precipitation increases. Wind is a different story. We are very sure about wind and hurricanes and tropical cyclones globally, and how tropical cyclone development is occurring it's not more frequently, but faster. It's not more frequent, but faster. And that is going to be a storm issue. When you're talking about wind generation, is very unclear, because some of our climate models are very, very good, are showing more wind in some parts of our generation areas in the West. Others are showing less. Some of them are showing jump ball. Well, when I'm a meteorologist and I see that, that tells me, yeah, we don't know yet. Mm-hmm. Solar's interesting because if you're already sunny, you can't get sunnier. But solar generation does become a little bit less efficient with hotter weather. That's a known quantity. So if you're in a hot area and your solar panel derates at a certain temperature, if you're going to experience that temperature more often, you're going to derate that solar panel a little more often. In terms of the amount of sun we're getting, though, unclear, because again, some parts of the globe might get cloudier, not sunnier, and it could be a very, very subtle difference of a few miles on who is getting cloudier and who is getting sunnier, depending on where you are near a water body. Very unclear at this point. I think the biggest thing, though, is that the forecasting, the day-to-day, the week-to-week weather forecasting for those renewables, the importance is already really, really high, and it's only going to go higher. Because as we get more, we rely more and more on that power to meet our energy needs.
Building off of that as well, understanding the challenges hydropower will face in terms of timing. I know that we've talked about it at great length on this podcast, for example. We talk a lot about, in the Northwest, the ability of hydropower to be used as a backup to other renewables. I know the pairing between hydropower and wind is really strong, for example. Does the dynamic for hydropower having to kind of shift, let's say late summer, hydropower is a little bit shorter on energy than it maybe would have been because there isn't as much water in the system at that point in time. Could that impact then if wind starts dropping off, for example, and you don't have as much of that hydropower to tap into as a backup?
It's really hard to say, and I think it's not so much a weather and streamflow question as it is how much you put in, and how much wind and solar do you put in and where. And then it becomes much less of a meteorology and hydrology problem and much more of a power planning problem. But that is something that needs to be addressed if you're going to put in renewables on a large scale that we really, frankly, do need to combat, putting more carbon in the atmosphere. It's a tough problem. Luckily, and this is what gives me hope, there's some really smart people working on this. So,
I think that's a perfect place to go next here, because what I really did want to tap into was the idea around the anxiety of climate. Uh-huh. So many people are concerned. You see the polling data that suggests that anxiety is only rising, and especially among younger demographics. I mean, it's almost kind of shocking when I read into it just how much even the generation below my own is extremely concerned about where climate change is taking us. For us here in the Northwest, should we be so concerned? Should we be so anxious? Or is there some good news that could maybe help ease those fears a little bit, at least in terms of our energy?
Great question, because I work with young people quite a bit in a couple of other roles in my life. Yes, they should be concerned. Yes, because they are inheriting this, and they're going to be dealing with climate change for their entire lives. Because even if we reverse now, even if we stop putting carbon into the atmosphere today, we have a certain amount of warming baked into the atmosphere that's going to have to go on now for a couple of decades. I am really glad to see younger people stepping up and making their voices heard, that we got to do something different here. The good news, and there's two good pieces of news. One is local, and that is we don't see the water scarcity issues that we're seeing in other parts of the world. We also we have to worry about sea level rise here in the Pacific Northwest, but we are not in a situation where major metropolitan areas, I'm thinking Florida, Louisiana, coastal Virginia, that are already pretty close to sea level and are dealing with land subsidence in addition to sea level rise, where they've got a real problem. We're a little more insulated from that. The best news I can say is that there are really, really smart people, smart young people that are wanting to jump in and help and do something. And I can't say enough, they're part of the solution. Younger people are part of the solution because they're the ones that are going to get the engineering degrees and the oceanography degrees and the hydrology degrees and the meteorology training and degrees to help solve some of these issues, and maybe even hydropower degrees to help us make this all work and to be resilient. I mean, you think about how many other challenges that humanity's had in a couple thousand years, and we've risen to every one. This one's going to be no different, and it's going to be a younger generation that's going to be part of the solution. So that's my hope.
And I think just to tack on to that as well, so much of that same kind of polling that's out there is showing how much maybe young people are sort of like throwing in the towel or quitting. And it's really encouraging to hear from you that for whatever portion of the population is all doom and gloom, that there's enough that are saying, okay, I'm going to do something about this, right? I'm not going to just, let this consume me and all that, but I'm going to take my time and energy and put it into solving this challenge and putting myself on the front line.
I'm going to use myself as an example because one of the reasons why I wanted to be a meteorologist since I was 5 was that lightning hit our house when I was 5. And I still remember it. It was a traumatic experience because we took a direct hit and half the light bulbs in our house exploded at once. And just completely weird, wild experience, and going, I want to learn about that so it doesn't happen again. Well, that naive, you're a 5-year-old, but that was one of the motivations for me to get into meteorology. And hey, these people need to be warned when these are going to occur. And well, wait a minute, that's a hard problem to. Well, I'm going to have to get good at math. I don't like math, but I'm going to have to get good at it. All right. And before I knew it, I was getting more and more into meteorology. That's the type of thing that I hope that can happen, where if younger people are feeling anxious about the situation we're in, you can either, some people it's very hard to deal with, but redirecting it for me would turn out to be the motivator for my career. So, I'm really excited to see some of the people that we've hired at BPA in recent years that are really interested and really understand that hydropower is also a green resource, and they want to be part of the solution and to leverage what we have here in the Pacific Northwest to not only keep our power rates as low as we can, but really help everyone along. And for all the people in all the places that use the Columbia River and have used it for thousands and thousands and thousands of years, let's help each other out. And if everyone's entering into that spirit, I think we're in great shape.
And I think that along those lines, I also want to bring up that when I was looking into your background and just getting to know a little bit more about you before this podcast, I also saw that you have this title of Power Services Intern Program Coordinator. And from the way you're speaking, I can certainly see why. I'd really love to hear more about what that side of your job looks like in addition to everything else we've discussed. And if you could share with the DAM listeners today how a prospective intern could learn about more opportunities that exist and get involved in BPA.
I'll be honest, Austin, this has been the biggest joy of my career. One of them is leading the program, although I'm starting to transition out of this role. But being part of the program for 12 years as we've been bringing in new interns and then leading it for the last 5 plus, that's been a really exciting thing because that intern program now is only hiring meteorologists and hydrologists, but we're also hiring engineers, economists, business analysts, math and science folks, and a lot of really smart people that we're bringing in from either universities or from that just graduated from universities into BPA, having them try us out as we try them out. It's basically an interview that goes on for 1 to 3 years. And to see them grow and to see them ask really good questions. And I love it when I get challenged and I'm like, darn, they're right. Awesome. That has been exciting. And we hire in power services, we hire 4 to 6 interns a year. Transmission also has an intern program at BPA. I have a counterpart that leads that. They hire as many as 20 interns a year. So we're constantly, I would say not constantly, we're always hiring usually during the between November and early January. We put the applications out or the requests out for applications. They're on our BPA website. And you can actually go to the bpa.gov website, click on the careers tab, and there'll be a section about internships. And then when we are actually advertising the internships, they go out on USA Jobs, just like every other federal job does, including mine someday. It'll go out on that USA Jobs website, and we invite interns to apply. And if you want to apply, you can actually set up your resume in the system now and have it ready to go, and you can tweak it and work on it over the course of months. And a lot of our new employees have done that, and they've stuck around. So it's great. We've kept them, and they've been growing and moving up. In a couple of cases, are now fellow managers of mine. That's really neat, and it's a great opportunity. So there's lots of ways to get involved.
Yeah, and I'll also add to that based on all the different things you're describing, it sounds like if someone's maybe not sure that their potential career path would intertwine with BPA, check again, because there's lot more. There's a lot more there than maybe they would realize as far as the different sort of roles needed for BPA to function and succeed.
I have a laugh about this because I work with the transmission organization quite a bit because of wildfire mitigation and also storm management and handling ice storms and winter storms. The class I hated when I was a meteorologist at university was electrostatics and learning Coulomb's law and how electrons move through materials. And I'm like, I am never going to use this ever, ever, ever again. And now here I am at BPA, and I have electrical engineers pointing out to me that, oh, guess what? That class is back. And I didn't think I would get into hydropower at all. When I went into meteorology again, I wanted to do television. Then went, oh, well, actually, no, I want to do National Weather Service and be part of the watch and warning decision-making process. Oh, wait a minute. Now, climate change is really interesting. Well, hydrology is really interesting. One thing that anyone that's listening on this podcast who are early career, mid-career, or late career, it's not too late. That you can, as you're going along, oh, wait a minute, I really like that too. Check it out. It might lead in a completely different direction. Might be a little awkward. Might feel a little scary. But getting into this business, there's a lot of entryways, and not the ones you typically would expect.
Yeah. As far as, kind of wrapping up today's conversation and, getting to the tail end here, do you have parting words? Do you have anything you want our audience to know, particularly about this subject or, anything else that maybe we didn't touch on? Just, is there anything else, anything you'd like to add?
I think the bottom line that I've really liked about working for Bonneville Power Administration and just working with a lot of great people in the region is that the Columbia River, federal Columbia River hydropower system is really a gem. And it's amazing how many good things it does, and we need to mitigate the issues that they did cause. And also acknowledging that there's a history here that's checkered. I think there's a lot of good people with good intent and goodwill that want to make this work in a way that keeps our power affordable, green, and a lot of smart people, not just at BPA, but elsewhere in the region, that are all working together to make that happen. That's been a lot of fun and continues to be. And we've got a lot of new people coming in that are also wanting to do that too. So that's great. So I think we should really be proud of the gem that we have.
Well said, and yeah, I think we're in good hands here, and maybe sometimes that's taken for granted or taken you don't fully grasp it, but particularly when you start to look to other regions of the country, you start to look at what energy looks like for folks outside of the Northwest, you realize we got it pretty good here.
Yeah, and that does not mean we don't have fundamental challenges. We do. And again, getting into the weather and streamflow space, the biggest challenge we have is climate change. But again, we've got a lot of smart people working on it to make this system more resilient and be able to handle this too. So I'm optimistic.
Yeah, I appreciate that optimism, and I appreciate everything that you've shared with me today, and everything that our audience will gain as a result of listening to this podcast. And along the lines of listening to this podcast, I'm not sure if you got to listen to any past episodes of Dan, including the one we did with Michelle. And no judgment if you haven't, because I know everyone's busy, and this is a very complex topic we're often talking about here, and one that not people always have the time to listen to, especially when it comes to intentionally listening and trying to actually pick everything up. But
sure.
One thing that we do here that we kind of put our guests on the spot a little bit with at the end of every episode, and some people appreciate it, some people are what the heck are you doing to me, man? But
all right.
I appreciate all perspectives, and I understand everyone's side of it, but we treat everyone equally here. So everyone gets the parting question. And based on how we kind of wrapped up the end of this conversation, I suspect we won't be struggling so much here. The thing I like to ask all of our guests is to give us a piece of life advice, and that can be about the topic, that can be career related, or it can just be something that speaks to you in your everyday life, or maybe something you discovered recently that really stuck out to you. But we like to do that, and the reason we like to do that is because we always want people to get to know who you are, right? We want people to not just understand the topic and everything, but also get to know the people behind our energy and behind hydropower. And so with that, the floor is yours.
The floor is mine. Okay. The thing that comes off the top of my head, because I've had to do this a lot recently, if you have a mentor that you've had for 10, 20, 30 years, don't be afraid to reach out to them again, because they have great wisdom and experience as they get more senior. And if you are not a mentor now, become one. And if you're 40 or 20 or 15 or 13 maybe even, there's someone that will benefit from your experience and wisdom. And being a mentor for someone and then being willing to reach out to your mentor, I think goes a long way, because there's a lot of people that can help guide you through this crazy path of life. And things are never going to go 100% right. They're just not. But having a few people to call in and say, hey, I'm dealing with this issue. How do you handle it? And they might tell you flat out, I didn't handle it well at all. Here's what I did. Don't do that. That's very valuable. And you always get more out of it than you give. So there's my advice.
I love it. And I'm really happy that you were able to make it here today, and happy to have you on the podcast. I think that today's topic as a whole, I mean, so incredibly important, and it's something that we're discussing so much, but we, at least here at Northwest River Partners on the Dam podcast, have not been able to actually dive this deep into. And so I'm glad we can finally do that today.
Great. Be careful about talking to weather nerds. We'll go into the weeds very quickly.
Well, maybe other people. I certainly enjoyed it. So thank you for being here. Really appreciate it.
All right. Thanks a lot, Austin.
A special thanks is owed to Eric for making today's podcast possible and for answering some important questions while also providing us the context and insights necessary to better understand the why behind his answers. I think we did a pretty good job today at determining the answer to whether or not hydropower can survive climate change here in the Northwest, but rightfully so, Eric pointed out that we still should be concerned about some of the challenges that likely lie ahead. At the same time, I hope his words aren't lost on you with regards to the silver linings of the situation. We have dedicated and incredibly bright minds working to find solutions to those challenges, and perhaps you might be among them or capable of joining them in this fight. But who am I to assume with any real certainty if we actually did address your questions and concerns today? Instead of making such assumptions, what I'd really love is to hear from you. I'd like to know what you think, and maybe we could even start a conversation. It's as simple as reaching out to us over at nwriverpartners.org and sending a message through our contact form. If that's too complicated, that's okay, because we also have an email address that you can use directly, which is info@nwriverpartners.org. Let me know what you thought of this episode or any others, and feel free to recommend future topics and guests as well. Or just let us know what you'd have on your mind. At the very least, it'd be great if you could share this podcast with your friends and family to help us grow and reach new listeners. Leaving a 5-star review on your favorite listening platform is a huge help as well. And while you're there, don't forget to turn on notifications so you don't miss future episodes, which arrive every other Friday. Lastly, be sure to follow us at NW River Partners on Facebook, Instagram, X, YouTube, and LinkedIn. Now, speaking of climate, spring has sprung here in the Northwest, and I hope you've all gotten some opportunities to get out and enjoy the sunshine. I'm off to do that as of recording this outro, so until next time, see ya.